Hello, everyone, and a very good evening, dear authors, session chairs, and invited guests. Welcome to Technical Session 6D. Myself, Samruddhi Mughal, and I will be the moderator for this session. On behalf of Global Knowledge Research Foundation and Geoscholastic, it is my great pleasure to welcome you to the 10th World Conference on Information Communication System, Software, Security, and Sustainability, London, UK. The 10th edition of the conference is being organized in a hybrid mode. The physical event was successfully held yesterday in London, UK, and the virtual event is being conducted through Zoom from 29th to 30th July 2026. I hope you all enjoy today's informative, insightful, and interactive technical session. In this session, we have six presentations. Each presenter will be allotted 12 minutes for the presentation, followed by 3 minutes for the question and answer session. I will give a gentle reminder when 10 minutes have elapsed to help you manage your time. I would also like to request all participants to kindly stay connected with us until the closing remarks of this session. If you have any queries or require any assistance during the session, please feel free to write to me in the chat box. Before we begin the presentations, I would like to introduce the distinguished session chair for this technical session. Firstly, we have Dr. Victor Aquinobola Olutayo. Dr. Victor Aquinobola Olutayo, a senior lecturer and head of the Computer Science Department at Venete University, Iloro, Ikiti State, Nigeria. With extensive experience in higher education across prominent West African institutions, his core technical research interest encompasses soft computing, service-oriented computing, IT service management, and data science. I'll request Dr. Olutayo sir to share their views with the presenters. I think there is a technical issue. We'll move forward with another. We have a second
Hello,
session chair.
can you hear me? Can you hear me now?
Yes, sir. I can.
Thank you very much. Once again, good afternoon, everyone. My name is Dr. Victor Olutayo, has been mentioned, and I'm happy to be here once again to be session chair for this World S4 Conference 2026. And briefly, we welcome our participants as well. And briefly, we want to inform all of them to respect time. Generally, each participant has 15 minutes. So therefore, they are going to use 12 minutes for their presentation and then the remaining 3 minutes for one or two questions. So, and I want everybody to respect the time. So once again, you are welcome. Thank you very much.
Thank you very much, sir. We have our next session chair, Dr. Namrata Nishant Vasatkar. Dr. Namrata N. Vasatkar is an assistant professor in the Department of Computer Engineering at Vishwakarma Institute of Information Technology, Pune. With over 12 years of experience, she has published more than 20 papers in national and international conferences and journals, and her expertise lies in the domains of artificial intelligence and data science. I may now request ma'am to share their views with our presenters.
Yeah, I'm audible.
Yes, ma'am, you're on.
Yeah, thank you. Thank you, Samruddhi. Good evening, all, everyone. Welcome to this technical session. So, I'm Professor Namrita, and it's my pleasure to serve as a session chair for this session. So, we have a series of interesting parties presentation lined up today. So, I request all the presenters to keep within the allotted time and encourage the audience to ask the questions after each presentation. Yes. All the best to all the presenters. Thank you.
Thank you so much, ma'am. Now let us begin with today's paper presentation. Uh, our first presenter is Ning Zheng. And the paper title is A Cost Model Audit of Project Leap Phase 2, Latency, Capacity, and Mitigation Safety in Post-Quantum RTGS. You may start your presentation.
Okay, so let me share. So can you see my screen?
Yes.
Okay, sure. So good afternoon, everyone. My name is Neng Seng. And this is a joint work with Liu. Now I will present a cost module audit of the project Leap Phase 2, latency, capacity, and migration safety in post-quantum RTGS. So this is the outline. Okay, so the real-time gross settlement system or RTGS system process high-value payment in central bank money. So these systems are among the most critical financial infrastructure, and their cryptographic production must remain secure not only today but for decades. And this is especially important because the payment message institutional communications may have long-term confidential. And quantum computing creates a serious challenge now. And a particularly important concern is that we have the harvest now, decrypt later threat. This means an adversary may record the encrypted financial traffic today and decrypt it in the future once large-scale quantum computer become available. And the project Leap Phase 2 demonstrated that the post-quantum cryptography can be integrated into a T2-like RTGS environment. However, it also reported a large verification latency overhead. So we have a central question here. So can PQC be deployed in RTGS without breaking latency, capacity, and migration safety? Okay, so this is the background. We will first introduce the two main post-quantum primitives relevant to this paper. So the first is the MLKM, which is FIPS 203. This is a key encapsulation mechanism. So in RTGS context, MLKM is mainly relevant for confidentiality and protection against harvest now, decrypt later attack. And the second is MLDSA, so which is the FIPS 204. And this is a digital signature scheme. In RTGS, the MLDSA is relevant for the authentication and the integration. And the project Leap Phase 2 tested crystal division for, which is closely related to the final MLDSA family, although not identical to the final NIST standard. And the project Leap Phase 1 started the quantum safe migration for financial system and to emphasize hybrid approach. And the project Leap Phase 2 moved the experiment closer to the production grade RTGS setting, especially to a T2-like environment. So the Leap Phase 2 reported that the PQC verification took approximately 209.9 milliseconds, while the RSA baseline took approximately 28.1 millisecond. So in the tested environment, PQC verification appeared to be about 7.5 times slower than the RSA verification. At the same time, the BIS and other standardization bodies recommend the crypto agility. So the existing reports do not provide a closed form latency and the capacity model for the RTGS deployment. Here are two technical traditions that in our paper. The first one is the hybrid cryptography. So we have the hybrid CAM, hybrid key exchange, hybrid signatures here. And the second tradition is the transaction safety. The RTGS system are not just cryptographic system, they are transaction processing system. So our contribution is to connect these two areas like the hybrid PQC migration and the latency bounded transaction compensation. Okay, here are our contributions. I will present it one by one. Okay, so the main idea of our paper is simple but important. The PQC migration becomes feasible for RTGS when slow verification is moved off the synchronous settlement critical paths. The project Leap Phase 2 showed that the PQC verification can be functionally integrated. But if every transaction waits synchronously for the full PQC verification path, the latency overhead becomes very large. So the main bottleneck is not only the cryptographic primitives, but it comes from the protocol envelope processing. Therefore, we argue that the asynchronous PQC verification can preserve compatibility while hiding the latency from the settlement. Okay, so first we will introduce the model of the synchronous design. So in this model, the total synchronous latency is equal to the network delay plus the expected verification time plus the ledger commit time. The key point is that every transaction waits for signature verification before the commit. And to use the LIPS report number, the PQC verification term is approximately 209.9 milliseconds, while the RSA verification is approximately 28.1 millisecond. So we have a factor of 7.5 times. And we have an alternative model is the asynchronous verification. Instead of blocking settlement until PQC verification finish, and the ledger can enter a bounded temporary state, such as the pending. The PQC signature is then checked by an asynchronous verifier in parallel with the settlement workflow. So we have two possible outcomes here. This idea is based on well-established mechanism in atomic commit protocol and compensating transactions systems. So we have a core question here. So how long can the temporary state safely persist? To answer this question, we introduced the watchdog timeout inequality. So here it means the T timeout is greater than the expected computation time plus 2 times the coordination latency plus the runtime variance. And this inequality ensures that the timeout decisions are not only based on the average latency, but also include a tail risk margin. Okay, so here we show that the timeout changes under different data assumption. It means the deterministic pipeline make timeout nearly independent of K. So a verification pipeline can make a synchronous rollback much easier to bound. Okay, so here we need to analyze the capacity. Okay, the first inequation is the synchronous throughput, and the second equation is the asynchronous offloaded throughput, and the last one is the latency height gain. Okay, so here we have an example. So in this example, the synchronous throughput is around 38, but the asynchronous offline is around 12,800 TPS. And these numbers are illustrative, but the conclusion is robust. If the full PQC verification envelope is placed synchronously on the settlement path throughout collapses, so it moved to a sideline verifier. Okay, so to check whether the cryptographic primitive itself is the main bottleneck, so we benchmark here. The benchmark was run on these platforms, and we tested the following algorithms. And the goal is not to reproduce the full LIP environment, but to compare primitive level cost with the LIP's full verification envelope cost. Okay, so this is the single algorithm result as shown here. So the key comparison is between the division 5 median verification and the LIPS reported PQC verification envelope. And the cryptographic core is only a very small fraction of the full measured path. Okay, so we also benchmark the hybrid constructions. So we have the nested hybrid signature and hybrid CAM here. And this result indicate that the hybrid mechanisms are not prohibitively expensive at the primitive level. Okay, so we then audit the project LIP phase 2 from a migration safety perspective, and we identify 3 main gaps. The first one is the hybrid signature was not studied but not tested. The second is hybrid CAM was not tested at the DEP layer. The third is the deployment rely on a modified schema connector. Okay, so let's introduce one by one. The first gap is that the hybrid signature will not test it. Okay, so the LibFace2 can see the hybrid signature conceptually, but did not validate them in the production grade gateway pass. So our purpose is to use a nested signature. We use an outer RSA plus an inner MLDSA. So for the outer RSA layer, so support the legacy compatibility, and the inner MLDSA layer provide post-quantum authentication. And for the second gap is confidentiality. The LibFace2 focus mainly on the BAH level signature, but signature do not protect message confidential. And for the harvest now, decrypt later tag, the quantum safe transport protection is necessary. So we propose a DEP layer hybrid CAM. The third gap is optional. The LibFace2 rely on a modified SMIC connector and vendor-specific PQC software. And this creates several concerns here.
Sorry
And
to interrupt.
Okay, so
Sorry
our
to
recommendation.
interrupt.
Okay.
Gentle reminder, you have only 1 minute left to conclude your
Okay, sure.
presentation.
Okay, so this is for the last gap. Here we have we use the add-only architecture here. Okay, so we conclude the three gaps. This is for the limitations for our work. And in conclusion, the quantum safe RTGS is feasible if the PQC is deployed as a bonded, asynchronous, and migration safe layer rather than a blocking critical path operation. So it means quantum safe RTGS is actually feasible. Okay, thank you.
Thank you so much, ma'am. Do we have any questions from session chairs?
Yes, Samruddhi.
Okay, ma'am, you can ask your question.
So, yes, I'm audible.
What do you mean, so available?
Yes, ma'am. Yes, ma'am, you're audible.
Can you go to your architecture slide?
Which one?
Architecture. Add only architecture.
Architecture.
Yeah.
So the last one, right? The
Yes, last one.
okay, add only architecture here. Okay.
So, what are the next one? Diagram.
Next one.
Architecture diagram.
Okay. So do I need to introduce the add-only architecture here? Okay, so here we propose an add-only architecture. The legacy SMIC and the RTGS core so remain unchanged here. So in parallel, the PQCSVS side lane verifies the inner PQC signature asynchronously. So
Yeah,
the confidentiality is handled at the DEP layer. And the authentication is handled through the nested BAH signature. And the PQC verification is handled by the asynchronous side lane service. So the architecture principle is to avoid modifying the most sensitive core infrastructure.
So my question is, what are the main advantages of the add-only architecture compared to the legacy RTGS architecture?
The advantage.
Yes.
Okay, so our advantage is not on the legacy as mistake because in this part, the legacy as mistake remains unchanged.
Okay, thank you.
Yeah, thank you.
Thank you, ma'am.
Yeah, thank you.
Let's forward to the next presentation. We have our next presentation, Shakib Abdullah, and the paper title is An Alternative Design Paradigm Using Distributed Approach for 112G Baud, Ultra-Wide Bandwidth, Electro-Optical TIA Receivers. You can start your presentation.
Okay. Good afternoon, everybody. Can you guys see my screen?
Yes,
Hello?
sir. Yes, sir.
Good afternoon, everybody. As the host mentioned, the title of my paper is an alternative design paradigm using distributed approach for 112 gigawatts per second, 112 gigabits per second NR0 224 gigabits per second PAM4 ultra bandwidth optical TI receivers. Yes, I know the title is long, but as we innovate more stuff, we have to add more uh, technical jargon to distinguish us from other projects. This project. This is something. This is actually an old project, almost 4 years old, 4 or 5 years old. But this was done in the industry at a company called Electrophotonic IC or ELPHIC. It no longer exists. It got bought out, and now it's called Info Indium Phosphide. But it's still registered under the actual name of Electrophotonic IC. Uh, it was in collaboration with Carleton University as well. That being said, I got permission to finally publish this. As you know, in the industry, they do stuff and then they allow us to publish once they moved on to better stuff, right? Whether it's Nortel back in the days or Sienna or whatever it may be. So I finally got to, I thought it'd be interesting. Initially, this was actually sent in publication for years ago at the optical conference, IEEE optical conference, but we had to take it out because they didn't want to publish it at that time. But now they gave us the green light to do so. And at that point, you can see in 2020, even in 2023, Elphic now says available with high-speed EML samples at 224 gigabits per second per lane for data centers. So basically, the optical industry almost had its own Moore's law where it was going, the speeds were basically doubling. The optical transceiver speeds were doubling, the fiber optics, the electronics at almost 2 times every 3 years or so. But when it came to right before COVID, 2018, 2019, we kind of hit a bottleneck where we were hitting technical limits in the way we were doing things, similar to how a transistor, you keep making it smaller and eventually gets the size of an atom, and you have all these quantum tunneling and all sorts of issues. So you cannot make the gate any more thinner, and everybody's struggling to. Moore's law is not holding up that much anymore. So for the longest time, we had some issues. Finally, last year, Marvell, Semtech, Sienna, they finally started rolling out their versions of 224 gigabits per second optical transceivers. Now, we already had the transmitters, you can see the EMLs, electro absorption modulator lasers, way back in this was not in 2023, we already had them before that. But you can't have a transistor without a receiver. It's pointless and it's useless, right? If you transmit the data, you also need the receiver. And so that's what we were working. I was part of the receiver team. Oh, I did some transmitter stuff, but the motivation behind this project was we needed a receiver that works at those speeds too. And everybody was stuck. Every company was racing to it. Unfortunately, back in the old days, you would have this feedback amplifier topology. Feedback amplifiers is great, and I'll explain soon enough in the next slide. But it no longer worked. I won't go into too much details. You look at the small signal models, the parasitics. This architecture hit a bandwidth limit. And so we couldn't get the speeds we wanted with this. Now, there was a way to get these speeds. Again, you need better technology, you need smaller transistors, and so on and so forth. And in our field, we tend to use 3.5 technologies over silicon a lot of the time because there's a lot of advantages with the pin diodes and lasers with the 3.5s over silicon. So we at that time there was something called distributed amplifiers. They use it in space and satellites and all sorts of stuff. We're like, why not use that approach with our optical front end TIA, the transimpedance amplifier, the receiver. And it turns out we did it. It's not new. It's Stackinger and stuff they've been talking about in the past. But we weren't hitting the speeds with feedback, so we decided to go with this, and it has good clean gain flatness. With this kind of technology, you really need really good gain flatness because it's ultra wideband. Ideally you'd want to go from DC 0 all the way to the Nyquist criterion, which is half of the gigabaud rate. But in reality, Stackinger suggests if you want to receive the signal cleanly, you want more closer to 2/3 or 0.7 times the gigabaud speed, which is in our case, the 224 gigabits per second PAM4, that's 112 gigabaud per second, times that will give you approximately 80 gigahertz. Now imagine 80 gigahertz, DC to 80 gigahertz. That's a huge, no amplifier usually does this unless you use certain like feedback or so on and so forth. We found that distributed amplifier, it's not perfect, but it was good enough, plus minus 3 dB, to give us that. The other thing is, obviously, in reality, you don't go to DC for DC offset cancellation, all sorts of stuff. So you want to cut off of 1 megahertz, and the reason for that is you don't want DC drifts, such as when you run long chains of zeros and one digits. You'll see that it starts drifting, and the receiver, the digital DSP, might signal it wrong. So for that reason, that's another challenge on the lower end. The upper end, you need the bandwidth. On the lower end, you lose the bandwidth too. So there was some trade-off, and also you need gain. As you add more stages in this, you lose bandwidth. So we have to come up with some gain bandwidth trade-off, and get as much bandwidth for as much gain as we can get. And this was obviously designed in the 3.5 semiconductor because our pin and our laser were designed in 3.5 semiconductor. I'm not going to show the results of the simulation in schematic because in this type of work, once you get to this field, it's no longer analog design, it's no longer microwave design, it's no longer optical design, it's no longer RF design. It's all three in ones. Everything you've learned in your electronics course, advanced electronics, microwave techniques, RF techniques, optical techniques, analog techniques, you have to combine everything and something called schematic driven layout or layout driven schematic. You have, obviously, you verify the schematic very quickly, but it's kind of useless. You have to, there's a lot of parasitics. And one of the advantages of this structure is we would design a little bit of layout schematic test, little bit layout schematic test, and so on and so forth, because we would absorb as a distributed amplifier. Basically, what it sees is all these LC sections. These are basically basically a transmission line. So you absorb the parasitics from these transistors and these metal interconnects and traces that connects the signals, and it looks like a transistor line with a certain impedance. Sorry for the markers. I have no idea how to get rid of them. I'll continue on for the sake of time. But excuse me, Yulisa, you're running. It's not me. Somebody's been running markers all over the place. So basically, if you can absorb the parasitics, then you can get higher speed. Can you please stop Yulisa from writing all over my presentation? Thank you. So that was the idea. We absorb the parasitic from the interconnected transmission line. That way, we can hit higher speeds than we can with traditional designs. And so that's what we did with this layout and so on and so forth. And you can see that it was all the parasitics, every interconnected was carefully chosen. Now at this point, we only had 0.8 micron tech for the indium phosphide. Now we have a little bit better. So we managed to go back to the feedback design for the 224. But then if you're the next evolution, which Google and NVIDIA wants for the data sensors and AI, they want 448 gigabits per second. Again, we're looking at this architecture for the push until the transistors catch up with it. And so this shows the electromagnetic extracted simulations. As you can see, it's relatively flat. We have our 1 megahertz 3 dB, and we have a little bit of peaking, yes, but it's not enough that it will destroy the eye and close all the PAM4 eye components. So it's good enough, and we're hitting 80 gigahertz of bandwidth. And obviously, with 80 gigahertz, that's a lot of noise. And this is not narrowband. This is full-on DC to 80 gigahertz, super ultra wideband. So when I did the simulations, we did it with transient on. We had the noise weight fully to 1. This is adjusted after you measure, so you can put 1.5, 0.5, depending on how you want to correlate with your measurements. But our noise bandwidth fully 112 gigahertz, noise time step 1 over the gigabit rate, 8.9 picoseconds. And you can see at negative 3 dB, I'm optical input power. It's still a pretty good eye. It's not as high amplitude as we wanted, but it's still decent. 30 millivolt peak-to-peak differential. Now, typically in the past generation, the 112 gigabits per second, the power levels were from negative 6 to plus 3. Obviously, if you double the speed, you double the bandwidth, you double the noise, you're going to lose 3 dBs of power, but they still want negative 6 dBm in the industry. But that's for another talk altogether. But it's still healthy, negative 3 dBm, and obviously you can go to plus 3 dB, no problem. Now there were some issues and troubles on the way, hiccups. These are some lessons learned from the past 4 years ago in the industry that I thought was useful. This eye that you see had realistic parasitics estimated. We had bond wires at the output. We had a bond wire at the input, although we planned to flip chip, then eliminate that parasitic too to speed up the process. We had real DC blocks as parameters in there. when we did them, and we did it at 25 to 75 C, with 55 being the typical normal data center temperatures. And you can see that just adding if you use real bond wire, external bond wire, you've lost the eye. If you
Sorry to
use
interrupt.
yeah,
Sorry to interrupt. A gentle reminder, you only have 1 minute to conclude your presentation.
thank you very much. You can also see that flip chip versus another long bond wire will screw it up as well. And you can see that even if PAM4 is not great, NRZ is you get the 9.5 dB signal to noise ratio improvement at half the bit rate. And just for you guys, since you guys hear the presentation, I left that company, but at that point, I left just when we got our chip, and I was doing a measurement on another project that I did. Unfortunately, I don't have a detailed view of the chip, but you can see one of our variants. It's right there, and you can also see the 224 gigabits per second, another variant. You can see the inductive choke that I have here, there. And basically, this shows this work. We were all struggling. All the industry was struggling to get that to 224 gigabits per second TIA. This work shows that by using a distributed approach, you can hit those limits. At that time, it was 0.8 micron tech. They've improved since then, but now we can use it to the next evolution of the speeds that's coming up. And that's basically it. Thank you very much. Any questions?
Thank you so much. Do we have any question from session chairs?
No question from my side, Samruddhi. Thank you.
Our second session chair. So, do you have any questions?
No question from my side too.
Okay. So with that, we'll move towards our next presenter. Our next presenter is Cicera MS, and the paper title is Bridging the Rural Digital Divide, a systematic review of ICT access and its impact on livelihoods, education, and health. You may start your presentation. Cicera, are you there? Ma'am, are you there? Ma'am, your audio is off. Yeah.
Am I audible now?
Yes, yes, you are audible. Please share your screen.
Is it visible, ma'am?
Yes, yes, it is.
Good afternoon, everyone. Myself, Shishra. It is my pleasure to present our research paper titled Bridging the Rural Digital Divide, a systematic review of ICT access and its impact on livelihoods, education, and health. This paper is co-authored by Nirmal Prabhu, Shishra MS, Kanagraj S, Kritika P, and Ashwin C. From the Department of Social Work, Amartya Vishwa Vidyapeetham, Coimbatore. The central theme of our paper is the rural digital divide in India. In this presentation, I will discuss what the digital divide means, why it continues to exist in rural areas, how information and communication technologies or ICTs influence education, healthcare, livelihoods, and governance, and what can be done to achieve meaningful digital inclusion. Moving to the conclusion part, the term digital divide refers to inequalities in people's ability to access, use, and benefit from digital technologies. Initially, the digital divide was mainly understood as a gap between people who had access to the internet and digital devices and those who did not. However, the concept has now become much broader. Today, digital inequality includes not only whether a person has an internet connection or a smartphone, but also whether they have the digital skills, knowledge, resources, and opportunities required to use technology meaningfully. In the context of rural India, the issue is particularly important because ICT has become increasingly connected with everyday life. Digital technologies are now used for education, healthcare, governance, etc. Therefore, when rural communities are excluded from digital technologies, they may also be excluded from important social and economic opportunities. This exclusion is influenced by several interconnected factors, including inadequate infrastructure, affordability of devices and internet services, limited digital literacy, gender inequality, caste, education, income, etc. are such as the barriers. Therefore, our paper argues that the digital divide should not be viewed simply as a problem of internet connectivity. It is a complex social issue involving economic, cultural, and institutional dimensions. And why is this topic important? In education, students increasingly depend on the digital platforms, online learnings, and internet connectivity. In healthcare, ICT can support access to telemedicine, health information, etc. In livelihood, digital platforms can help rural communities access market, employment opportunities, etc. And in agriculture sector, farmers with information related to markets, weather, agriculture practices, and other services. In governance, citizens can access government schemes and public services through digital platforms. Therefore, digital inclusion requires more than simply providing infrastructure. It requires an environment where people have access, affordability, skills, confidence, support, and meaningful opportunities to use technology. And moving to the objectives of the study has 4 major objectives. First, the study aims to examine the causes of digital divide in rural India. We wanted to understand why digital inequality continues to exist even with improvement in digital infrastructure. Second is this study reviews the availability of ICT access, digital skills, and patterns of technology usage among rural population. Third is the study assesses the impact of ICT on important areas of rural life, particularly education, healthcare, livelihood, and governance. And finally, the study identifies the major socioeconomic barriers that prevent inclusive digital participation and provides a recommendation for developing more inclusive intervention. Therefore, the overall purpose is to understand digital divide from a broader and more people-centered approach. And moving to the literature review part, earlier studies primarily focused on the questions of whether people had access to technology and internet connectivity. However, more recent research shows that access alone is not enough. The digital divide now includes 3 important dimensions: access to technology, the ability to use technology, and the ability to achieve meaningful outcomes through technology. The literature also show that socioeconomic factors play an important role in the digital inequalities. Factors such as caste, gender, income, education, geography, and social background influence people's ability to participate in the digital ecosystem. And however, one important gap identified from the literature is that many studies focus heavily on the infrastructure and access, while relatively less attention is given to the deeper social and structural causes of digital inequality. And moving to the methodology part, we use Van Dijk's resource and appreciation theory. This theory helps us to understand that digital inequality is not created only by the absence of technology. People need different types of resources to benefit from digital technologies. These resources include factors such as material, educational, social, and cultural resources. The person may also require digital literacy, education, language, skills, confidence, social support, and institutional assistance. This theory perspective is important for our study because it supports our argument that simply expanding internet infrastructure is not automatically eliminate digital inequality. And moving to other methodology, for this study, we adopted systematic literature review using mixed method approach. Then for data sources, we use corpus in the peer-reviewed journal articles and conference proceedings. This study considered literature published between 2010 and 2026, primarily focused on the digital divide in rural India, including both qualitative and quantitative studies. For the screening process, we followed PRISMA guidelines, and the literature was screened through different stages, including screening, abstract screening, and full text screening. After the screening and selection process, total of 61 research articles are included in the final review. And there are five major indicators. These indicators were access to technology, usage and digital skills, positive outcomes of benefit, impact on social and economic opportunities, socio-economic and demographic factors. Then moving to the Prisma diagram, Prisma provides a structural approach for identifying, screening and selecting relevant research studies. And through this systematic process, we selected 61 research articles for the final review. The purpose of using Prisma was to make literature selection process more transparent, systematic and reproducible. Moving to the thematic evidence table, we examined the selected studies based on the five major themes that I already discussed. And the table shows that these themes are interconnected. Therefore, the digital divide cannot be understood through a single factor. It is multidimensional issue involving technological access as well as social and economic conditions. Moving to the result, the first major findings relates to access to digital technology. Our review indicates that broadband and internet infrastructure have improved in many areas. However, improvements in infrastructure have not completely eliminated in rural digital divide. One major issue is the affordability of digital devices. Even when internet connectivity is available, some rural households may not be able to afford digital devices. There are also continuing gaps in connectivity and electricity in some rural areas. Therefore, our findings suggest that infrastructure is necessary, but infrastructure alone does not guarantee digital inclusion. And next is usage and digital skills. The literature indicates that digital literacy remains relatively low among sections of rural population. This means that even when people have access to smartphones or internet services, they may not be able to use digital technologies effectively. The problem is particularly significant among women and marginalized communities who have faced additional social and structural barriers. Language is another important challenge faced by the people. In addition, limitation in training and insufficient institution support can prevent people from making meaningful use of digital technologies. And next is positive outcomes of and benefits. Literature indicates that digital technologies can create several positive outcomes for rural communities, such as education. Digital technology can provide access to online education, etc. Healthcare, ICT can improve healthcare information and support digital remote healthcare services. Third is financial support. Digital technologies can make financial services more accessible, and agriculture productivity. Farmers can improve their access to information and services, and therefore ICT has a potential to contribute significantly to rural development. And moving to the social and economic opportunities, digital technologies can create new opportunities for employment and entrepreneurship. They can also support self-help groups, allowing members to access information, networks, financial services, and market. ICT can improve access to e-governance services, enabling rural citizens to interact with government services more easily. And therefore, ICT has a potential to reduce geographical limitation and create new social and economic opportunities. However, unequal access to these technologies can also create new forms of inequality. Therefore, digital inclusion should be considered an important component of inclusive rural development. And moving to the socio-economic and demographic factors, our findings also show digital inequality is strongly connected to socio-economic and demographic factors. The major factors identified are gender, education, income, caste, geography, and language. Gender is an important because women may experience unequal access to devices, and education influence a person's ability to understand, and income affects whether individuals can afford digital services and digital things. Caste and social inequalities can also influence access to digital resources. Geographical location is another important factor because remote and rural areas may face weaker connectivity. And finally, language can become a barrier when digital services and contents are not available in locally accessible language. These factors are interconnected and together they contribute to unequal digital participation. Moving to the discussion part, the findings of the systematic review demonstrate that rural digital divide is a multi-dimensional and interconnected issue. Our study shows that the digital divide extends beyond simple access to technology. It includes inequalities with digital skills, patterns of usage, and ability to individuals and communities to obtain meaningful benefits from digital resources. ICT has created significant opportunities in areas such as education, healthcare, governance, agriculture, financial inclusion, and rural livelihoods. However, these opportunities are not equally distributed. Despite government initiatives promoting digital inclusion, rural communities continue to experience unequal access and participation in digital ecosystem. And therefore, the digital divide should not be addressed through a single intervention. Instead, we need to integrate approach that combines infrastructure development and affordable access, digital literacy, inclusive policies, and community-based support. The ultimate goal should not be simply to connect people to the internet, but to ensure that they have participate meaningfully and equitable in the digital ecosystem. Moving to the policy implication and recommendation part, based on the findings of our systematic review, we propose several policy recommendations. First is expand last mile broadband connectivity, improve the affordability and device or and internet services, establish community digital resource centers, strengthen digital literacy programs, develop local language and digital content, empower women through ICT training, collaborate with self-help groups and Panchayat Raj institution. Finally, the digital inclusion should be integrated into livelihood, education, health, and governance programs. This will ensure that digital technology becomes a tool for overall rural development rather than isolated technological intervention. Moving to the conclusion and future research part, to conclude, our systematic review demonstrate that the rural digital divide extends far beyond the availability of digital infrastructure. Socioeconomic inequalities continue to play a major role in determining who can access, use, and benefit the digital technologies. Meaningful digital inclusion requires a combination of infrastructure, affordability, digital skills, and institutional support. And therefore, policy should move from an infrastructure-centered approach towards a people-centered approach. The objective should be to ensure that rural communities are not only connected to digital technologies, but are also empowered to use these technologies to improve their education, healthcare, livelihood, financial opportunities, and participation in governance. Ultimately, bridging the rural digital divide is essential for achieving inclusive and sustainable rural development. Moving to the future research, there are several areas where future research can contribute to a deeper understanding to the rural digital divide. First is longitudinal study can examine how digital inclusion changes over time, and regional comparison can compare digital inequalities across different states and rural regions of India. And third is future studies can examine relationship between artificial intelligence and digital inclusion, particularly where emerging technologies reduce or increase existing inequalities. Then next is like women and vulnerable population who may face multiple and overlapping barriers to digital participation. And finally, future research can evaluate the effectiveness of existing government digital inclusion initiatives and identify areas where implementation can be improved. To conclude, bridging the rural digital divide is not only simply about providing internet connectivity, it is about ensuring that every individual has the resources, skills, affordability, support, and opportunity to participate meaningfully in digital world. A truly inclusive digital society can contribute to better education, improved healthcare, stronger livelihoods, greater financial inclusion, and more effective governments. Uh, Thank you for your kind attention. I am happy to take any questions. This was the
Thank
some
you.
of the selected. Yes, ma'am.
Uh, yeah, continue.
Okay, this was some of the selected references. Thank you.
Thank you, ma'am. Do we have any question from session chairs?
Yes, ma'am. My question is, Your study highlights the improved education and healthcare as positive outcomes, right?
Yes, ma'am.
Could you share one practical example which support these findings?
Like nowadays, it's e-learning and online platform education is more important after like COVID time. Then it's more important in educational sector.
Okay. Yes. Thank you.
Well, can
Sir,
you hear
do you
me?
have any question?
Yes. Thank you for your presentation. Though it's a review paper, but it would have been much more better if you have actually stated the empirical value of some of those papers you review in terms of those key factors that you have used to measure this digital divide within the environment. For instance, if you want to say that the usage is low, how do we know that the usage is low without having an empirical value that have been verified, that have been stated that, oh, within this also value to so value is what we have for usage for certain group of people. Okay, so it would have been much more better, because if you just go to an environment and you see that, you just look at what they are doing and just say the usage is low, there must be an empirical value that will state that definitely that have been verified by other people. It's just an advice for further research work on this type of topic. Thank you very much.
Thank you, sir.
Thank you so much, sir. Thank you so much, ma'am. With that, let's move to our next presenter. We have our next presenter, Hemlata PG, and the paper title is Hybrid Energy Based Thermoelectric Cold Storage for Sustainable Vegetable Preservation. You may start your presentation.
Yes, ma'am. Am I audible?
Yes, go on.
Yes, yes.
Uh, uh, so, good evening, judges, session chairs, and fellow researchers. According to the Food and Agricultural Organization, nearly one third of the agricultural produce globally globally lost post harvest, with smallholder farmers bearing the heaviest financial burden in rural region. So, ha- so to solve this critical challenge, our team has come up and developed a powered cold storage system. Today, we present the hardware design, solar charge control logic, and empirical trial results of our functional prototype. Welcome to our presentation. Our work focuses on leveraging clean solar energy and thermoelectric cooling to provide an affordable grid cold storage lifeline to farmers. So, the problem statement with this is that the post harvest loss, up to 20 to 30% of the harvested grains, fruits, and vegetables spoil due to ambient heat and humidity, and also the rural power grid constraints. Conventional vapor compression cold storage requires high power and continuous electricity. Rural power cuts and high utility tariffs make them inaccessible to small farmers. The core problem in agricultural supply chains is post harvest decay. Perishable products like tomatoes, carrots, and capsicum decay rapidly when exposed to ambient temperature. Farmers cannot rely on conventional compressors based refrigerator. On our project addresses this gap by creating an autonomous, clean, and cost effective solar cold storage system. So, the main objective of our project is design and implement a microcontroller based solar charge controller with multi stage changing, integrate a reliable Peltier based thermoelectric cooling assembly with proper insulation and airflow management, evaluate system performance under varying environmental conditions, and track real time produce shelf life. To address these issues, our objective were fourfold. First, design an efficient microcontroller driven charge controller that regulates voltage and prevents battery degradation. Second, integrates a solid state Peltier cooling mechanism. Third, ensures off grid battery capability to zero grid reliance. And fourth, conduct real world trials on produced freshness over extended time periods. So, the system architecture and workflow. The block diagram illustrates our system architecture. The 12-watt solar power generates DC power, which is fed into our custom charge controller. An Arduino Uno monitors system parameters via voltage sensors and manages battery charging status. The stored energy power three parallel 12-volt parallel modules fitted with the heat sinks and fans inside an insulated cabinet. An SMPS interface is also provided for dual input operational flexibility where grid power is available. Hardware specification that we have used are being presented here. We have done the testing on the charge controller performance. In the morning, system operates in the bulk mode, stepping up low panel voltage from 10.2 to 17.5 volts. Peak solar noon 1:30 transition is absorption mode, voltage boosted to 36.3 volts. Later afternoon, 3 to 5 pm, enters the float mode with 14.45, maintaining full charge while protecting the battery against overcharging. Cold storage prototype design. The cold storage prototype design shows the thermal insulation, forced air circulation, target temperature control. So the experiment freshness of the proposed system is as presented here. So the capsicum fully spoiled, severely wrinkled by day 5 is shown here. We have tested our system with the real-time temperature all the with these three of the vegetables being tested. To validate our system, we placed identical samples of capsicum, carrot, tomatoes under ambient air conditions versus inside our cold storage system. The visual and structural results are conclude. Item left at ambient temperature suffered severe moisture loss, fungal decay, and wrinkled by day 5 and were completely spoiled by day 13. In contrast, items stored inside the Peltier cold chamber retained high, fresh, and minimal cost loss. So the project impact and the conclusion is successfully built an off-grid eco-friendly solar cold storage box for small-scale agriculture, prolonged produce freshness by 2 to 3 times compared to room temperature ambient conditions. In conclusion, our solar power cold storage system prototype successfully proves that clean, low-cost thermoelectric cooling can drastically lower post-harvest losses for rural farmers. This technology offers a scalable, sustainable solution to boost agricultural income and food security. Thank you, and we are open for the questions.
Thank you, ma'am. Do we have any questions from session chairs? Sir, do you have any questions?
Yes, I'm saying that for this topic, sustainable vegetable preservation, does it have a range of time? For instance, this preservation, does it take, is it that for life you can preserve it for as long as it exists? For how many years? For 100 years? So how sustainable is the preservation is my question.
So, sir, as the harvest is taken, when we sell those harvests, we suffer the losses as many of the farmers form the same product and sell it for the lower price. So, this cold storage with the low cost can provide a sustainable lifeline by providing more 4 to 5 months of lifeline for the harvest so that the farmer can get more of the profit from their harvest. So, the main intention of our project is to reduce the post harvest losses, sir.
All right, thank you.
Thank you, sir.
Thank you, sir. Thank you, ma'am. With that, let's move towards our next presentation. We have our next presenter, Jovan Kurnivan. The paper title is Intelligent Prediction of Employee Attrition using data-driven analytics. You may start your presentation. Hello, do we have
Am I
Jovan?
hearable?
Yes, yes, you are audible. You can start your presentation.
My screen is already shared. Okay.
Yes, your screen is visible.
Okay. Good afternoon, everyone. My name is Jovan Kurniawan, and today I will present our study entitled Intelligent Prediction of Employee Attraction Using Data-Driven Analytics. This research focuses on how data-driven analytics, especially machine learning and explainable AI, can help organizations predict employee attraction and understand the reason behind the prediction. The study was conducted by authors from Bunda Mulia University, Sampurna University, and STMIK Palangkaraya. Employee attraction is an important issue for organization because when employee leave, the company doesn't only lose people, but also lose knowledge, experience, and team stability. In many organizations, predicting employee resignation is difficult because HR data is usually imbalanced. Most employees stay, while only a smaller number resign. Because of this, standard machine learning model may show high accuracy, but actually fail to detect employees who are at risk of leaving. Another problem is interpretability. If a model only gives a risk score without explanation, SR team may find it difficult to decide what action should be taken. Therefore, prediction alone is not enough. The model also needs to explain the reason behind the prediction. Most previous attrition prediction models treat all employees in the same way. They assume that the factors causing a resignation are similar for every employee. However, in reality, junior and senior employees may respond to the different workplace pressure. Younger employees may be more sensitive to salary, overtime, or immediate workload, while senior employees may be more affected by job satisfaction, role meaning, and long-term career development. Another gap is that many studies focus only on prediction accuracy but do not connect to the prediction result with precision retention strategy. This study addresses the gap by combining prediction explanation and decision support recommendation. This study has three main objectives. First, we aim to build an interpretive machine learning model for employee attraction prediction. The model should be not only predict whether an employee is likely to leave, but also explain the factor influencing that prediction. Second, we handle the class imbalance problem using random oversampling apply only to the training data. This is important to help the model learn more from actual resignation case. Third, we use SHAP to explain the risk driver and translate the result into decision support recommendation for HR. In this way, the model can support more targeted and evidence-based on retention strategies. The methodology follows a structured XAI-driven pipeline. First, the HR data goes through pre-processing, including label encoding and encoding for categorical variable and scaling for numerical variable. Second, random oversampling is applied only to the training partition to balance the number of resignation and non-resignation case. This step is important to avoid data leakage and maintain the validity of the testing process. Third, XGBoost is used as the predictive model because it can capture nonlinear pattern in organizational behavior data. The model is optimized using recall and F1 score because in attrition prediction, missing employees who are actually at risk of leaving is more harmful than simply maximize accuracy. Finally, SHAP is using to interpret the model result at both global and cohort-specific level. The dataset was structured as a flat analytical base table, so it could be processed efficiently for machine learning. In pre-processing, outliers were not removed automatically. This is because unusual behavior in HR data, such an overtime spike or unusual work pattern, may actually indicate potential resignation risk. To address class imbalance, the study used random oversampling Unlike synthetic approach, random oversampling duplicate real attrition case rather than creating artificial employee profile. The main goal is strategy are to reduce false negative. In other words, we want the model to be better detect employee who may resign, instead of only predicting the majority class, which is employee who stay. XGBoost was selected because it is effective in capturing complex and nonlinear relationship between HR variable. Employee attrition is rarely caused by one single factor, so a model that can capture iteration pattern is needed. In this study, the optimization focused on recall and F1 score rather than raw accuracy. This is because high accuracy can be misleading in imbalanced dataset. After the prediction process, a SHAP is applied to explain how each feature contributes to attraction probability. SHAP provides both global explanation and individual level explanation. In addition, the analysis is stratified by age group to identify demographic difference between the young and senior employee. This helps reveal whether the same factor affect different employee group in different way. The results show an important trade-off between accuracy and resignation detection. The baseline random forest model achieved high accuracy, but its ability to detect actual resignation case was weak. This means model looks good statistically, but was less useful as an early warning system. After applying random oversampling and optimizing XGBoost, the model achieved a recall of 0.824 and F1 score of 0.702. This indicates that the model became more effective in identifying employees who are likely to resign. For HR decision making, this is more useful because the purpose is not to classify employee correctly, but to detect risk early enough so that intervention can be made. The SHAP analysis identified three main global driver attraction risks, which we refer to as a burnout triad. These are monthly income, overtime, and job satisfaction. Monthly income reflects the compensation factor. Employees with lower income or perceived pay gaps may have higher resignation risks. Overtime reflect workload pressure. Frequent overtime may increase fatigue and dissatisfaction, especially if it's not balanced with a proper compensation or support. Job satisfaction reflect the emotional and psychological side of work. When employees feel less satisfied with their role, environment, or career development, their attraction risk may be increased. Together, these three variables explain the main upward pressure on predicted resignation risk. The edge stretch sharp analysis show that attraction drivers are not uniform across all employees. For younger employees, compensation gaps and overtime spike have stronger effect. This means junior employee may react more quickly to immediate transactional factors such as salary and workload. For senior employee, the pattern is different. Their attrition risk is more influenced by job satisfaction and role meaning. This suggests that senior employee may be more concerned with a long-term role value, professional recognition, and meaningful contribution. This finding is important because it shows that one general retention program may be not effective for all employees. Retention strategies should be adjusted based on employee characteristic and risk driver. This study concludes that combining random oversampling, XGBoost, and SHAP can improve employee attraction prediction while keeping the model explainable. The random oversampling balanced XGBoost model improved the detection of potential resignation, while SHAP helped explain the reason behind the prediction. The results show that retention strategy should be differentiated between junior and senior employee. For junior employee, organizations should be prioritize compensation, equity, and workload control. For senior employee, role enrichment, job satisfaction, and meaningful engagement are more important. Overall, this framework support a shift descriptive HR reporting towards prescriptive and human-centered HR governance. That concludes my presentation. Thank you very much for your attention. I very welcome comments or suggestions regarding this study.
Thank you, sir. Do we have any question from session chairs?
Yes. Thank you for your presentation, Mr. Presenter. In your methodology, yes, you use data machine learning models for your data, isn't it?
Yeah.
So how many of them did you use? How many machine learning did you combine to make up your model?
3.
3 of them.
Mm-mm.
3, right?
Yes.
Good. So at the end of it all, which factor do you now discover that actually causing employee attrition more than every other factor in your results? As a result of the model and output, which factor is causing attrition in your data analytics?
I'm sorry, can you repeat the question? I can hear it clearly. Or maybe you can text on the column section. Or maybe.
Hello, can you hear me?
Yes.
Hello?
Yes, yes.
Can you hear me?
Yeah.
You mentioned some drivers that are actually causing employee attrition, like monthly income, job satisfaction, and stuff like that. I said, which variable or which factor you think is having much percentage that is causing this attrition based on your analysis?
Okay. Well, so, based on SHAPU summary plot, job satisfaction is the single largest overall factor as it sits at the very top of feature hierarchy, together with the overtime and monthly income. These are three from the burnout rate, which drive the majority of predicted attraction risk across the organization. The top one, I think, is job satisfaction. Hello, sir?
Hello, sir. Are you there?
Yeah, I'm here.
You want me to repeat my question, or you already hear it?
No, I'm okay. You have responded.
Thank you, sir. With that, we'll move towards our next presentation. Our next presenter is Ida Julia Presta, and the paper title is Urban Intelligence and Digital Twins for Adaptive Urban Governance. You may start your presentation.
Good afternoon. Okay. Okay. Good evening, everyone. I will present our work on urban intelligence and digital twin for adaptive urban governance. This is a multidisciplinary research effort by Interdepartmental Center for City Science that explore how cities can govern growing complexity using advanced digital tools and a new form of urban intelligence. Contemporary cities are shaped by climate change, digital transformation, demographic growth, socioeconomic inequalities, and environmental uncertainty. These dynamics challenge a traditional static planning approach, which struggle to capture the dynamic interaction between environmental, social, technological, and economic processes. This motivates the search for new governance paradigms that are adaptive, data-driven, and cognitively aware. We interpret the urban system as a complex adaptive system, following Holland's notion of network of interacting agents producing emergent behavior. Urban components like infrastructure, people, institution, economic, and information flow interact in non-linear ways, generating feedback, adaptation, and self-organization. As a result, small change in, for example, population distribution or infrastructure capacity can have a disappropriately large impact on congestion, accessibility, and resource consumption. To address this complexity, we introduce urban intelligence as a framework for adaptive and cognitive urban governments. Unlike many smart cities approach focus mainly on optimization and efficiency, urban intelligence emphasizes the cognitive dimension of urban system. The city is seen as a dynamic environment where data, institution, and citizen continuously interact to produce collective knowledge and guide decision. Within this paradigm, the urban intelligence digital twin is conceived not simply as a digital replica of the city, but as a cognitive infrastructure. It integrates heterogeneous dataset, simulation models, real-time monitoring, and participatory process into an undefined environment for knowledge production and decision support. This allows planners and institutions to evaluate alternative scenarios, anticipate risk, and adapt strategies dynamically. A key requirement for operational urban intelligence is semantic interoperability. Cities generate huge volumes of heterogeneous data from sensor, administrative system, mobility platform, and social media and geospatial infrastructure, often with an incompatible format of classification. Urban ontology organizes this knowledge into a shared categories of actor, object, and process, enable coherent integration of data across domain and scale. These concepts are illustrated through the case studies in Italian cities such as Matera, Milan, and Ginosa. In Matera, the digital twin became a governance infrastructure. The GIS evolved into a platform integrating data and stakeholder and decision-making process. With the social layer treats structure. In Milan, the Smart Path app incorporates experience-based evaluating accessibility, comfort, public space, quality into an algorithm model, while in Genosa, school children map home school routes, turning perceived safety and daily needs into a criteria from planning priorities. This example converge in the WISH project, which developed as an urban intelligent platform where the digital twin acts as an advanced decision support system. The platform is organized from all of the data come from the different cities like Matera and Catania, collected in the data lake and in the WebGIS and semantic layer. With the ontology, we build three different thematic digital twin, for example, digital twin of mobility, digital twin of environment, or like DT air or DT hydrology, and the social layer means the data from the citizen science. All of this data are elaborated from the DSS platform. The urban intelligence platform is organized in a multi-layer level architecture. lower layer integrating a data source such as IoT sensors, smart infrastructure, territorial database. Intermediate layers manage data acquisition, quality and integration. Upper layer host analytics, simulators, and the DSS. The platform uses scalable data lakes with geospatial extension like PostgreSQL or MongoDB. WebGIS interface and toolkit like PTVism orchestrate via microservices and REST API with robust security and access control. We propose a 4C model: cognizant, commonality, construction, and caring as a conceptual structure for resilient and cognitively enabled governments. Cognizant refers to a multidimensional urban knowledge and continuous learning. Commonality to a shared knowledge accessible to multiple actors, and construction to a co-creating and simulation of scenarios, and caring to continuous monitoring, alerts, and adaptive management. In conclusion, we frame urban intelligent digital twin as adaptive cognitive infrastructure rather than statistic representation of cities. We argue that the urban forecasting and control should be treated as a meta-learning problems. Digital twin should learn how to select, combine, and adapt model across stakes and under non-stationary condition and uncertainty. Decision support systems are the four core cognitive components, embedding data, simulation, and governance in feedback loops that enable evolving, learning urban intelligence system. I would like to thank the research team and the institutional partners who support this work and the related fixed experiments. For more information about the project and the activities of our Interdepartmental Center of City Science, please visit the website indicated in the final slide and contact us through the email address. Thank you for your attention.
Thank you so much, ma'am. Do we have any questions from session chairs?
No, I don't have a question from my side.
Thank you so much, sir.
Thank you.
As we come to the end of the technical session, I would like to sincerely thank all our authors for their excellent presentation and valuable contribution. I also extend my heartfelt gratitude to all the participants for being a part of this international conference. I hope today's session has been informative, engaging, and enriching for everyone. On behalf of the entire team, we thank you for your continued support during the 10th edition of World S4 2026, as well as throughout the previous 9 editions of the conference. We look forward to welcoming you again to the 11th edition in 2027. All presenters will receive their digital certificates via email within 2 working days. The conference publications will be available within 7 to 8 months. We kindly request your cooperation with the World S4 2026 team throughout the publication process. I would also like to express my sincere appreciation to our session chair, Dr. Victor Akinbola Olutayos sir, and Dr. Namrata Nishant Vasatkar ma'am for successfully chairing this technical session. I would like to request sir to kindly share their remarks.
Well, thank you very much. It's nice to participate in this OS Conference 2026, and it's nice sharing this particular session. And I look forward to another partnership in the future. Thank you very much.
Thank you so much, sir. On behalf of World S4 2026 Global Knowledge Resource Foundation and Earth Partners, please accept this certificate as a token of our appreciation for your valuable support and contribution. Thank you once again for your valuable presence and participation. This concludes our session. Before we end, I kindly request everyone to switch on their cameras for a quick snapshot of our virtual conference.
I apologize right now. My camera's not available.
Okay, no worries. Give me 1 minute.
Question for you. Are we going to receive a copy of the publication once it gets published?
Yes, sir. You asking question?
Yeah. Once the publication gets published, are we going to receive a copy of that?
Yes, you'll
The
receive a copy.
final publication?
Yes. With that, I'll conclude that the session is end. Thank you so much and take care. You may leave the
Okay, thank you. Bye.